Hey folks, for the second video of 3.2, we're going to talk about choosing the right system. This video has the purpose of helping you understand why the systems you see in some of our problems are named that way. And, should you choose to continue to study science or engineering, choosing the right system can make solving your problems much easier or much more difficult. So we start with just a little statement here. The identity of the system reveals what type or types of energy are present. So you will do a lot of choosing of a system very easily in most of our practice problems. When we do a lab, it might be a little difficult, but what really is the part that I want this video to teach you the most about is when you are asked a question about a specific system, I want you to be able to know what that means and how to interpret the name of the system and what to do with it. So I chose for this video an inclined plane. Now I chose it for two reasons. First reason is it's complex enough so that you will probably be able to see all of the complexities of energy conservation. The other reason is because inclined planes are generally difficult for students when they study them in forces, and mostly because of trig. And so I want to present you another way of looking at this inclined plane. And in certain situations, you'll be able to choose energy analysis over free body diagram and kinematics analysis. So there we go. So we'll examine a ball rolling down a hill with an initial velocity of v naught and a final velocity of v. The angle of incline is theta. So we start with a free body diagram because in order to apply conservation of energy, we have to verify that the system is closed. This one is not. These two forces point in two different lines, and so there's no way that the normal force and the force of gravity not only would have the same magnitude, but they would also be equal and opposite to one another. So the net force on this system cannot be zero. If there was friction, it could be zero, but that's actually going to present other complications. This system is open. Okay, so let's think about what that means. From our knowledge of forces, gravity is the force that's going to cause things to happen. So gravity causes the ball to speed up. Okay, and that's like from the forces perspective, that's what happens. Now, if I look at this situation here, I have v naught and v, and what I know about inclined planes is what I said. The value of v is going to be greater than v naught. This system is open, and so there is going to be a change in energy. And I just want to think about what that is. Well, the ball starts with some amount of kinetic energy here, and because it's moving faster, it ends with more kinetic energy. And that ends up being the change in energy. So in this system, when the system is just the ball, the change in energy is equal to the change in the kinetic energy. As we'll talk about in just a minute, that is the only type of energy you can consider here. If I want to talk about a reason, I'm going to say that gravity adds energy to the system. I'm going to say this now. When you are done with this unit and you're like nearing the end of 3.4 and you're trying to like fit everything together, come back to this video and see if some of these statements mean more to you after you've been through the unit, and see if you can see where I'm avoiding the use of the word work because you haven't learned it yet. All right, so this might like leave some questions, like why didn't we just talk about potential energy? We just learned about it in the last section. Why aren't we using it? That is because if it's just the ball, single object systems cannot store energy. Remember in the video for potential energy, energy can only be stored by a force, and so without another object in the system, there can't be a force between two objects in the system. It takes two objects to have a force, and so it also takes two objects to store energy. The value of gravitational potential energy for this single system is just 0. And because it's always 0, the change in value of gravitational potential energy is 0. Okay, so if the system is a single object, then only kinetic energy can you consider. As soon as we add another object, then we can start to have more complex analysis here. So same system, now we're going to analyze both the ball and the Earth. I'm going to redraw the free body diagram for the ball. I'm not going to draw the theta in there. Now let's talk about Newton's third law. If the ball is getting pushed up and to the right by the Earth, then the Earth is getting pushed down to the left by the ball. Those angles are off. I don't know why. Anyway, so those, I know why. The normal forces should be in opposite directions because that's how normal forces work. They push each other, the objects push on each other directly. And then gravity is also a third law force because all of them are. If the ball is getting pulled down by gravity from the Earth, then the Earth is getting pulled up by the gravity of the ball, and those forces have to be equal and opposite. If you enjoy that geometry notation, you can apply it to these two things. The normal forces are equal and opposite, the gravity forces are equal and opposite, and if I were to compute the net force for this system, it would be the upward force of gravity on the Earth minus the downward force of gravity of the ball. These would have to be vectors, and then that's in the y direction, and then that would be 0. Let's say y, and then the net force in the diagonal direction, that would be the parallel direction, would be the normal force on the ball minus the normal force on the Earth, and that would be equal to 0. I violated some vector math there. I apologize. But you can see that these forces would cancel and these forces would cancel for the entire system. This system is closed because the net force on the whole system is 0. So now we have a conservation of energy system. Two object systems can store energy and release it. And so potential energy is something that factors into this. It can change and it can cause things to happen. If I go back to this diagram, I can relabel it in terms of energy. If I'm allowed to consider potential energy, then I would take a look at this bottom of the ramp and I would say that gravitational potential energy is 0 right there. What that means is at this beginning position, this ball starts with gravitational potential energy because it is higher up than this lowest point, and it also begins with kinetic energy because it's moving. When I get the ball down to the bottom of the ramp, it's now at that UG equals 0, and so there is only kinetic energy. And so I can use that and I can write an equation that relates the energies here. That equation is going to look something like this. If I can assume that the gravitational energy or the mechanical energy is constant, then I can say that at the outset, the ball Earth system has both gravitational potential and kinetic energy, and at the end, the system only has kinetic energy. So what does that mean? Well, that means that this gravitational potential energy became part of the kinetic energy. If these are equal, then the final kinetic energy is going to be bigger, and that gain in kinetic energy is equal to the loss of gravitational potential energy. The gain in kinetic energy is equal to the loss of gravitational potential energy. So the change in kinetic energy is positive, the change in gravitational potential energy is negative, and so they are equal and opposite to one another. So what can we say? We can say, like, gravity transformed gravitational potential energy into kinetic energy. All right, so that's one way in which we talk about the events of energy. Now I have one more thing to do, and we have a graph of energy. It got cut off. This axis should say time. Later we'll talk about like time and distance graphs and how they would be shaped differently, but for now just energy. And I wanted to show you like how I would graph this data, how we would graph like, okay, the gravitational potential energy went away, the kinetic energy increased, and all the while the mechanical energy was constant. So I'm going to label this in 3 different colors. Because I identified that the mechanical energy was constant, I'm going to draw a flat line at the top of the graph, and that line is going to represent mechanical energy. The next thing I can do is say, well, the kinetic energy started at not 0, and then it ended as the only type of energy existing for this system. So I know that it's going to end here, and I also know that it's going to begin above 0. So I'm going to draw a line like this. So over time, the kinetic energy increased from this small value to this large value, where it was actually equal to the total energy. The last part of this is gravitational potential energy. Now, the total energy has to be constant, and so I'm going to just kind of look at the dots on my graph here and say, well, if the kinetic energy was 2 dots up from 0 at the beginning, the gravitational potential energy should be 2 dots down from the mechanical energy. So it started with more, for my fictitious graph here, more gravitational energy than kinetic. And then because of the way this problem goes, I know the gravitational potential energy ends at nothing for where I set up my 0 line. So I draw this last line, and the gravitational potential energy graph would look like that. So there's something to like keep in mind with this. The kinetic and gravitational energies change at the same rate in this problem. Now, they don't always have to do that because there are more types of energy around in the universe, and it's not always like a one-to-one change. You might have 3 or 4 different types of energy by the time you get to the end of this course. So in this situation, they have to always change at the same rate, and they have to mirror each other when they change. And so this is your most conceptual video of this section, where we deal with a lot of things having to do with open and closed systems and conservation. Thanks.